So first, we'll focus on the thermodynamic or the voltaic efficiency. So the thermodynamic or voltaic efficiency essentially is how much energy do I get out in a discharge cycle versus how much energy I have to put in during the charging cycle. So that essentially defines the cycle efficiency. And in a non-aqueous lithium-oxygen battery, what we have is we have lithium reacting with oxygen to form lithium peroxide as a product. And as I told you, the charging cycle, you oxidize this lithium peroxide, get oxygen and lithium back out. And what is important to note is that in this non-aqueous lithium-oxygen battery, this lithium peroxide that you have, the product is insoluble in the solvents that are used. The typical solvents used are dimethyl ether and things like that. So in ether-based solvents, lithium peroxide is insoluble. So what that means is we have a very interesting problem where the effect of the catalyst particle itself that is used to do this reaction is sort of not important. The reason for this is because you have something that is insoluble, what happens is you have your catalyst particle and you start to grow on this catalyst particle. In a typical reaction, you would have the product diffusing away, but here, because it's insoluble, it starts to coat the surface and you grow thicker and thicker layers of this film. It's essentially lithium peroxide film. And sort of the cleanest way to see this is the following experiment. This was done by Brian McCloskey, who's somewhere in the audience. So the experiment is the following. What I show here is a capacity plot. So what is plotted here is the voltage that you measure versus lithium metal on the y-axis, and capacity, essentially charge on the x-axis. And so these are constant current experiments. So this is essentially a time axis. So this is how long have I discharged this battery. And what is really interesting is that, so this is just carbon. This is gold on carbon, manganese dioxide on carbon. And beyond this, the initial nucleation phase, where you will definitely see some part of the catalyst. After that, the features are almost universal, independent of what catalyst you use. And so this, at least in at least a clean way, shows that the effect of catalyst is not important beyond the nucleation phase. So that means that what we have that determines the thermodynamic efficiency of the cycle is essentially growing of lithium peroxide on the discharge cycle and the etching of lithium peroxide on the charging cycle. So what we would like to do is essentially understand this process. And so what are the ingredients that we need to model this process? So there are essentially three ingredients that are there. We have electrons that need to come, and we have lithium ion that needs to come, and oxygen that needs to come to the reactive site, and they all need to react to form lithium peroxide. So how do we think about this? This is an extraordinarily complex problem because we need some way to handle the free energy of lithium plus in solution and this electron and things like that. But what we're saved by the fact that this lithium plus an electron is in equilibrium with lithium metal at the anode. So what that means is, from a calculation standpoint, we can essentially make this problem tractable by relating the free energy of these two species to the free energy of lithium metal. And then if we assume that there are no transport losses associated with oxygen, then we can start to understand the thermodynamics of this growth process. It's sort of my one slide to show that we sort of know what we're doing. Density functional theory is known to be notorious for describing oxides. And so what I show here is a calculated heat of formation versus an experimental heat of formation. And what is put here is a whole host of superoxides, peroxides, and oxides. And this would be the y equals x line when you have perfect agreement between theory and experiment. And there's a slope of about 0.9. But at least what this shows is that there's reasonable trends that one can extract out when we try and study these oxides and superoxides. So what we want to do now is to try and understand the fundamental electrochemistry associated with the formation of lithium peroxide. So at the anode, we appeal to the equilibrium condition that sets the free energy of lithium plus an electron to the free energy of lithium metal. At the cathode, we have a sequential transfer of lithium plus an electron to oxygen to form LiO2 first. And note that the surface site is on an already nucleated film of lithium peroxide. So you have a nucleated film of lithium peroxide, and then you grow on top of it. And then you add another lithium plus an electron to this, and so you form you form lithium peroxide. So this is basically repeating of lithium peroxide on top of the nucleated film of lithium peroxide. So the problem of this is essentially a problem of crystal growth. Problem of crystal growth is very complicated, and that's because there's a whole host of paths that one could take to grow. What I show here is some of those paths. So what one could do is nucleate on a terracite. So this is nucleating on a terracite to grow. You could diffuse from a terracite to a step site and then nucleate there, or you could diffuse from a step site to and go to a king site and nucleate there. But in electrochemical crystal growth, what we are after is essentially the ones that have the lowest over potential, because those will be the ones that are dominant in rate. Because when you apply a galvanostatic condition, those are the ones that have the lowest voltage penalty that one needs to pay. Those are the growth modes that will be active. Similar story during charge. You want to etch away on a terrace, or you want to etch away on a step, or you want to etch away on a key. So what I will show here is a representative set of overpotentials that we have calculated on a terrace, step, and a kink. And we calculated a whole host of structures, and the trends that I will discuss are sort of true across different sort of structures of lithium peroxide. Okay. So before I go into this description, I want to introduce a concept that I will use over and over again. So I'll go over this a little slowly. What is plotted here is a free energy diagram. And so on the y-axis you have free energy, on the x-axis you have reaction coordinate. And so here I have 4 lithium plus and 4 electrons and 2 oxygen, and the final product I have is 2 units of lithium peroxide. This is just because the unit cell of lithium peroxide has 2 formula units of lithium peroxide. Now, what happens when you run a reaction is this you now see a voltmeter here, and this is 0 on the scale of lithium plus. So at 0 volts versus lithium plus, it's downhill in free energy to take 4 lithium plus and electrons and oxygen and go to lithium peroxide. So this is essentially the energy we get out as electrical work in a battery. Right? So what we want to do is to try and understand what is the potential at which this reaction scheme is still downhill in free energy. So that's the process that we want to understand. And so what we do is we sequentially add lithium and electron to oxygen, so you form LiO2, and so you calculate the free energy of this state. Now, then you sequentially add this, and then you essentially have a free energy diagram. Now, what changes across the free energy diagram is essentially the number of electrons associated with that reactive state. Right? So the number of electrons here is 2, the number of electrons here is 3, number of electrons here is 4. And when you change the electrode potential, all you change is essentially, or to a first order, all you change is the free energy of the electrons. When you change the potential by a factor U, then you change the free energy of the electron by minus EU. So what happens is when you change the potential, you shift the free energy of these different states. And so what happens is you shift these free energies by different amounts, and there comes a potential beyond which the scheme is no longer downhill in free energy. Right? So what this means is this is essentially a thermodynamic limit for this reaction scheme to run from reactant to product. Right? No doubt that there could be other kinetic barriers and things like that, but this could sort of give you a really good initial idea of what are the overpotentials associated with this process. And what we found, and what I'll hopefully convince you, is that this analysis sort of takes us very far in trying to predict things. Now, the story is similar when you want to charge. When you want to charge, this thing goes down further, and it is the highest potential at which the reaction scheme is downhill in free energy to go from product to flow. So that's sort of the charging cycle. So what's interesting to note now we focus on what's the overpotential associated with growing on a kink site. Now what's really interesting is that you can discharge at a kink site at a very, very low overpotential. Right? This is sort of, this is of order 0.1 volts, and so this is very, very interesting because what I originally told you was all these bad things about optional electrochemistry with protons, where you have all this 0.4 volts overpotential, and even on the best catalyst here, we seem to be able to nucleate at a kink site at very low overpotentials of order 0.1. Same story under charging. We can charge on a kink site at around 0.9. The story is extremely similar on a step site. On a step site, you can once again grow with very small overpotentials of order 0.1. Same thing during charge. You can charge of order 0.15. When you go onto the terrace side, it gets a little bit more complicated. When you want to discharge on a terrace side, you're sort of breaking the extended stoichiometric surface. So what happens is you have to pay a larger voltage penalty to grow on the terrace. But at least there are growth modes in the kink and the step that are of low overpotential. And so those will sort of dominate in relevant current regimes. And so this is all. So the theory points to the fact that we should observe low overpotentials. What does the experiment say? So what I show here is a linear sweep voltammogram. So what is measured here is the current, and the voltage is spec. And so you measure the current and the equilibrium potential. So that's the potential at which lithium plus and oxygen is in equilibrium. So that sits at around 2.8. So what is seen is that there is a reduction feature, an oxidation feature at low overpotentials. But this field was sort of bitten once when such analysis was used to declare rechargeability of these batteries. So unless you couple the coulometry, which is essentially counting of electrons, to actually what is consumed and what is produced, you cannot conclusively say that this is the reaction that is happening. Right? And so this is exactly what our collaborators at IBM did, Brian and Alan. So what they do is they couple the voltammetry to a DEMS, which is a differential electrochemical mass spectrometer. So what they can pick up is what are the gas products involved, and what are the what's the rate of consumption of oxygen, and what are the gas products involved. So consumption during discharge and evolution during charge. And what you can extract out of this analysis is something very interesting, which is electrons per oxygen. Right? If you had perfect chemistry, then you only need 2 lithium plus and 2 electrons to form lithium peroxide. Right? So if you form perfect chemistry, then you would have essentially 2 electrons per oxygen. And this is indeed what we see during discharge. And during charge, we sort of have almost 2. Then it starts to deviate out. And so this actually, we'll come back to why exactly this deviates out like this. But what is at least seen is that the electrochemistry is the electrochemistry of generation of lithium peroxide and then etching of lithium peroxide. Now, we want to take this analysis and take it one step further and sort of try and understand what's the rate dependence of this. So what we want to do is to try and see if we can run this at high rates. So this is galvanostatic discharges that are run on a flat electrode, and this is different current densities. And in this case, 20 microampere per centimeter square. This is 1 centimeter square electrode. So in this, 20 microampere per centimeter square corresponds to about 20 milliampere per centimeter square in a real battery, because in a real battery you have all these like porous media, and you can essentially enhance the surface area by a factor of 10 to the 3. So essentially 20 milliampere per centimeter square essentially corresponds to about a 20 microampere per centimeter square corresponds to a 20 milliampere per centimeter square battery. And what's seen is the equilibrium potential sits around 2.85. What's seen is at 20 microamperes, the initial electrochemistry starts very, very early. So you have an overpotential that's associated of about 0.1, 0.2. We'll come back to these other features a little later. So what's at least seen is that the initial electrochemistry is really good on discharge. What about charging? Charging has a very similar story. We initially start out with extremely good electrochemistry. And so one can take these and then carry out what's called a Tafel analysis. And so you can essentially study how much voltage penalty that you have to pay to go higher and higher up in current density. And so this is experiment and theory that's put on the same footing. You essentially need to assume a certain density of peak sites, step sites, and terrace sites, which we can get by calculating thermodynamics of different states. And what's really interesting is the thermodynamic cycle efficiency is essentially the distance between the discharge and the charging curve. And so we essentially want to be off order 1 here. And so theory predicts a distance of about 0.3. Experimentally, they see a difference of about 0.4. So actually very interesting is that these two actually go back and go back to this reversible point, which essentially shows that it's actually one electrochemical step that's rate determining. There's also some other nice features that you can see. There's this nonlinearity that we observe. This nonlinearity essentially comes from a transition this is transition from growth on a step site to a terrace site. I told you earlier that terrace sites had a large over potential, and so in order to transition from the step site to the terrace site, you have to pay a higher penalty, and that penalty is a lot less during charge. You in fact even see those features in the experiments where you essentially see a much broader what's called a Tafel slope, which is essentially the slope of this line. You have much worse chemistry under discharge than charge. But the take-home message essentially is that the cycle efficiency of this battery is really good because you only pay a penalty of about 0.3 and you get about a 2.8 volt pattern, right? So that's remarkably high electrochemical efficiency compared to what we have with oxygen and proton, where you pay a 0.8 volt penalty for something that only gives you about 1 volt. So that's so what that means is at least the cycle efficiency is really good.